The accepted way to present a new assignment to the Center for Instructional Support's Programming Rovers is in a PowerPoint slide like the one I'm about to show you, and that I will send each one of my TAs by email to use as a reference and also to copy and paste some of the slides. The presentation page, what is the course number, what is the assignment, and the identification, the name of that assignment. This page is the same in all of our assignments, general policies about the number of attempts the students given per question, etc., etc., etc. About these random variables, in every exercise, one or more of the parameters will be different for every student that takes the assignment exercise. For each one of those parameters that will be different for each one of the students, we define what is called a random variable, and we define them like this: random variables for this question. This is assignment 5, question 1. Here is a description of the question, and here the random variables are, these are, and vs, the value of the source. And we specify what is the range of possible values for that variable. R is in the interval between 1 and 20 in steps of 1. So that means 1, 2, 3, 4, 5, 6, 7, all the way down to 20. And Vs is in the interval between 3 and 20 in ones by ones. That is all the integers between 3 and 20, including themselves. If the interval had been, in this case at the top, let's say 2, 1, 20, 2, so that would be 1, 3, 5, 7, 9, 11, 13, etc., etc., all the way up to but not surpassing 20. We have defined, and the programmers already have a subroutine for the parallel operation that is represented by this operator. When you write something like A parallel with B, the programmer will call that subroutine to perform A times B divided by A plus B, of course. The slide or slides of the question, all of them have the identity of the question at the top, like this: assignment 5 dot question 1 in this case. The slide or slides of the question have several parts. Identify the first one, question. Second part, the random variables. Then the answers, the weight of the question in marks, and the figure or figures for the question. Let's read the question. In the circuit in the figure below, obtain the output voltage V0, this voltage here, in volts, and the current I0 in milliamps, this current. Observe, in WeBWorK, every time you ask the student to find a value, you need to specify in what units to simplify the life of the programmer of WeBWorK. Enter V0 in volts and the current I0 in milliamps. This exercise attempts to erase the misconception that the output current of the op-amp is 0. That is almost never true. The values are R equal, brackets are kilo ohms, and Vs equals bracket Vs volts. Everything except the brackets is going to be typed just as text by WeBWorK on the screen of the student. Now let's see who are these R's and those square boxes around. In an exercise, there are some parameters that will be randomized. Every student will get different values of it. In this case, this resistor's value and that voltage source value are randomized. And R is given in kilo ohms and Vs is given in volts. For them, we specify the programmer that he or she needs to create two random variables, R and Vs. And we also tell the programmer what's going to be the valid range for those. So R is in the range between 1 and 20, taking 1 by 1. So that means 1, 2, 3, 4, 5, all the way up to 20. If this one, the step, had been 2 instead, the allowable values would have been 1, 3, 5, 7, 9, 11, 13, etc., all the way up to 20, but not exceeding 20. VS is in the range between 3 and 20, taking 1 and 1. And then the parts of the answers. The answers are formulas to obtain I naught and V naught. The answers the student needs to find as functions of the random variables that you have chosen for the specified problem, in this case R and Vs. I naught is a function of R and Vs, and V naught is also a function of Vs and R. Observe that the formula has been adjusted so that it renders milliamps. The weight is 30 marks, and here is the figure for that exercise. Now let's have a look at the obtention of the answer formulas using Maple for one another question. For this question, assignment 5, question 6. In the circuit in the figure, I'll show you the figure in a moment. R is brackets R. What does it mean? Brackets R. It means the value of the variable R that's been defined down here, all right? So that will appear on the screen of the computer as maybe 4, 5, 6, 7, 8, 9, 10. One of those values will appear here. And we tell the student those are kilo ohms. Compute and report the output voltage V naught and the output current I naught in milliamps. Let's have a look at the figure. This is the figure. There is only one randomized parameter R, and for that we ask the programmer to define one variable R in the range between 4 and 10, taken one by one. Now, how do we find those formulas? In this case, formulas for V naught and I naught in terms of R, the only one random variable. What I do is I use Maple. You are welcome to use some other tool like Mathematica or Wolfram Alpha or something like that. Now we solve the circuit. Identify every node. The reference node has been chosen for us. Choose the direction for the currents in every branch. 0 amps for the input of the op-amp. It's an ideal op-amp after all, and then we write the equations. NF for negative feedback, KCL for node number 1, and KCL for node number 2. Observe that I identify, I label every equation in the system. Why? Because we will need those names when I solve the system of equations using Maple, the symbolic mathematical solver that is available to everybody in our department. Maple. Now we are in Maple, which is available in every workstation in our department. In Maple, I write first the command restart. That makes sure that all the internal memory of Maple, every buffer, is cleared. And now we have a clear template to start writing. NF. Observe that colon equal is the way to define a name. NF is defined as V1 equal to V2, which is an equation. I'm calling NF, defining that name NF as the equation V1 equals to V2. KCL2, KCL1, colon equal, defined as another equation, which is 6 minus V1 divided by 4 kilos. When we're doing this kind of problems, don't try to save time doing things as if you were doing that by hand. I mean, do not cancel out kilos or millis or all of that. So write them explicitly. Also, I prefer to use integers. So a voltage like 0.7 volts, I write that 7/10, and I get very nice round numbers. That is equal to V1 minus V naught divided by 1,000 times R. You say, why 1,000 times R? Because R as a variable is given in kilo ohms. To turn that into ohms, I need to multiply that by 1,000, of course. KCl2 is V naught minus V2 divided by 8,000, and that is equal to V2 divided by 12,000. And those are the equations I need to solve. How do we solve that? With the command solve. Solve, and in parentheses we'll specify what needs to be solved. First, the system of equations in curly brackets like that, and then in another set of curly brackets, what unknowns I want to solve for. Well, the equations I want to solve are NF, KCl1, and KCl2. And the unknowns are, of course, V1, V2, and V0. Enter, and those are the solutions of those voltages, which will come as functions of R, of course. To find I0, this one, we compute the current in the 10 kilo ohm resistor, which is V0 divided by 10,000. We add the current in the bottom positive feedback resistor of the 8,000 ohm resistor, which is V0 minus V2 divided by 8,000 ohms. And we add the current at the top, which is V0 minus V1 divided by R. The sum of those three currents, according to KCl, is the current I0 leaving the op-amp, which we need to compute. The current I0 is the sum of three currents. This one, that one, and the one on the top. That is V0 divided by 10 kilos, the current through the load, the current here on the far right, plus the current at the bottom, which is V0 minus V2, which is going to be V1, of course, according to the negative feedback equation, divided by 8 kilos, plus the current at the top, which is V0 minus V1 divided by R. By the way, the R we're going to be using is 1,000 times the R specified by the problem. So we should say this time 1,000, that time 1,000. Let's write that in Maple. To capture this vector of solutions, I will go back here in front of solve and put a variable that is defined as that vector. X defined as the result of the solve function. So X is a vector. X brackets 1 is the first element of that vector. X brackets 2, and so on and so forth. If I take one of those, I use the function operand, and I say what operand of that expression I want. I want the second operand of the expression x sub 1, and look what I get. What I get is this one, which is exactly what we want. And why do I want what? So that I define variables I will use in computing I0. There are our variables: V1 calculated, V2 calculated, and VO calculated. Those are not the same variables that we used in the solution. Those are unknowns. Those are flexible. These are names we are using, defining them with the result of the solution this way. And now we can compute the output current. I0 is defined as V0 calculated divided by 10,000 ohms plus the current at the bottom, V0 calculated minus V2 calculated divided by 8,000 ohms, and the current at the top, V0 calculated minus V1 calculated divided by 1,000 times R. Why 1,000 times R? Because R is a number given in kilo ohms. So in this expression, we need to write everything in ohms. That's what we do. And that is the current I0 in amps. However, the student expects to see the value in milliamps, so let me multiply all of this by 1,000. 1,000 times that multiplies parentheses all that expression, and now I have I0 in milliamps, and that is the expression we're going to give the rovers, the programmers of CIS, so the Center for Instructional Support of the Faculty of Applied Science. We go back here, and that is exactly what we are providing. The solution already in milliamps, and using R in kilo ohms are V0 30R divided by 3R minus H. That comes directly from our solution here, V0. And the current I0 is computed this way. And that is a way to prepare a question for WeBWorks in AppSci.